Good morning, students. In this lecture series, let us move to applied physics, where focus is on bridging theory with practical applications to prepare us for a dynamic future in engineering and technology. This course moves beyond theoretical concepts, diving straight into how physics principles drive the innovations we see every day. Applied physics truly is the foundation of engineering. Physics provides the fundamental backbone for all engineering sciences, offering the essential principles that drive modern technological advances. Think about it. Everything from precise laser microsurgery to the complexities of space vehicles, and from the everyday computers we use to our mobile phones, every single innovation relies on core physics concepts. This course gives us the understanding to not just use but to create the next generation of technology. Our comprehensive study is structured around five critical areas: 1. Lasers and fiber optics; 2. Quantum mechanics; 3. Electronic materials; 4. Semiconductor physics; 5. Dielectric and magnetic properties. Each unit is designed to build upon fundamental principles, ultimately explaining the technologies that are shaping our modern world. Let's briefly review the learning objectives for each unit. Unit 1: Explore quantum behavior. Identify the dual nature of matter and understand particle behavior through quantum mechanical principles. Unit 2: Understand band structure. Explore solid band structures and classify materials based on their electronic properties. Unit 3: Master semiconductor devices. Acquire knowledge of semiconductor devices and their applications in science and technology. Unit 4: Compare material properties. Compare dielectric and magnetic properties to enable design applications in various fields. Unit 1 focuses on lasers and fiber optics. The term laser is an acronym for light amplification by stimulated emission of radiation. This revolutionary technology was theoretically laid out by Einstein in 1917 and first physically realized by Th Meinmann in 1960 with the development of the ruby laser. Today, the combination of laser technology and fiber optics forms the essential backbone of our modern communication systems, allowing for high-speed data transmission over vast distances with minimal loss. This enables the global internet and virtually all modern digital communication. What makes laser light so useful are its four unique properties. Highly directional. Laser light travels in one direction with an extremely narrow beam width, which is why it can travel long distances without spreading out. The divergence is calculated by the formula shown. Highly monochromatic. Laser light is a single frequency source. For high sensitivity lasers, the bandwidth can be incredibly narrow, as small as 10 to 8 O, a stark contrast to 1000 O for conventional light sources. Highly intense. Surprisingly, a small 1BW Heine laser can be more intense than sunlight. This high intensity is due to its coherence and directionality, with intensity being proportional to N2A2. Highly coherent. This is crucial. Coherence means there is a predictable correlation of amplitude and phase between any 2 points. This enables both temporal and spatial coherence, making it perfect for applications like interference and holography. Laser operation is governed by three fundamental quantum processes. 1. Stimulated absorption. An atom in the ground state, E1, absorbs an incident photon, gaining energy, Ken E2 E1, and transitioning to the excited state, E2. The rate depends on the number of atoms in the ground state and the density of the incident photons. 2. Spontaneous emission. The excited atom spontaneously returns to the ground state, emitting a photon of energy Hn. This process is independent of external energy and produces incoherent radiation. 3. Stimulated emission. This is the key process for laser action. An external photon strikes an excited atom, inducing it to emit a second photon. Crucially, this second photon has the exact same phase, frequency, and direction as the incident photon. This coherent process is what enables light amplification, or LASER. To ensure stimulated emission dominates over stimulated absorption, a special condition called population inversion must be achieved. This means that more atoms must be in the excited state, N2, than in the ground state, N1, N2, N1. This condition is absolutely essential for laser operation but contradicts the natural Boltzmann distribution. Normally, N1 would be greater than N2. We use artificial methods called pumping to create this inverted condition. It's also important that the excited state is a metastable state with a lifetime greater than 10 to 8 seconds. This stability is what allows the population inversion to be maintained long enough for the stimulated emission to effectively amplify the light. There are four main methods, or pumping mechanisms, used to achieve population inversion. 1. Optical pumping. This is common in solid lasers like the Ruby and indeed YAG lasers. A xenon flash tube provides broad spectrum energy that the laser material absorbs to excite the atoms. 2. Electrical discharge, used for gas lasers like He and CO2. A high voltage electric discharge excites the gas atoms through collisions with accelerated electrons. 3. Chemical pumping. In lasers such as the HF and DF lasers, a chemical reaction directly generates the excited states, providing the necessary energy for inversion. 4. Injection current. This method is used in semiconductor lasers like InP and GAAs. Electric current is injected across a PN junction, creating population inversion specifically among the minority carriers. The Ruby laser holds a special place in history as the first operational solid-state laser developed by Mainman in 1960. The active medium is a pink ruby rod, which is a crystal of Al2O3, aluminum oxide, doped with a small percentage of Cr3 plus chromium ions. The construction includes a resonator formed by two highly polished parallel ends, one fully reflective and one partially reflective, along with a xenon flash tube for optical pumping. This is a pulsed laser operating at a red wavelength of 6943 Or. In contrast to the pulsed Ruby laser, the Hene laser is a continuous wave device, also discovered in 1960 by Javan. It uses a 10.1 mixture of helium and neon gases. The operation is unique. A high voltage electrical discharge excites the helium atoms, and this energy is then transferred to the neon atoms via atomic collisions. The laser tube generates three primary wavelengths, but the most important is the 6328O visible red output. This bright, stable red beam makes the Hene laser an ideal choice for everyday laboratory applications, such as alignment and holography. The semiconductor laser is the type you'll find in CD players, fiber optic transmitters, and many consumer devices. It's essentially a specially fabricated PN junction that emits coherent light when forward biased. The emitted wavelength is directly determined by the bandgap energy of the semiconductor material, given by the formula Latour-Chun 2400 EGO. Their primary advantages are their compact size, high efficiency, simple construction, and the ability to control the output easily with current. However, they do have some drawbacks, including a large beam divergence and generally poorer coherence compared to gas or solid-state lasers. Lasers have truly permeated every sector of modern life, with applications across numerous industries. Communication. They are the heart of optical fiber systems, providing the high bandwidth needed for the internet. Their high directionality is also critical for space and submarine communications. Medicine. Lasers enable incredibly precise surgical procedures. For example, pulsed neodymium lasers are used to treat liver cancer, while argon and CO2 lasers are used to treat various organs. Industry. In manufacturing, high-power CO2 lasers are used to precisely cut and drill materials like metals and ceramics. They are also used for welding and testing the quality of various fabrics. Military. Lasers are used for laser ranging, which functions similarly to radar, providing detection capabilities. More powerfully, high-energy lasers are being developed to destroy aircraft and missiles. Moving to fiber optics, the optical fiber is essentially a thin, transparent waveguide that transmits light signals. The reason light is such a good information carrier is its incredibly high frequency, around 10 to 15 Hertz. This allows it to carry vastly more information than lower frequency waves like radio or microwaves. The fiber itself has three layers: a core with a high refractive index, N1, a cladding with a lower refractive index, N2, and a protective outer jacket. The fundamental principle of light transmission here is total internal reflection, which only occurs when the core index is greater than the cladding index, N1 and 2. Let's look closer at total internal reflection, TIR. TIR is what keeps the light trapped inside the fiber core. It happens when light moves from the optically denser medium, core, to the rarer medium, cladding. Three conditions must be met for TR. 1. Light must move from a denser to a rarer medium. 2. The core's refractive index must exceed the cladding's N1, N2. 3. The angle of incidence I must be greater than the critical angle, TC, which is given by sin 1, N2, N1. When these conditions are met, the light is perfectly reflected back into the core, guiding it along the fiber. When launching light into a fiber, two key parameters are the acceptance angle and the numerical aperture. The acceptance angle, AI, is the maximum angle at which external light can strike the fiber face and still be guided by total internal reflection. The numerical aperture, NA, is a measure of the fiber's light gathering ability. For light entering the fiber from air, the NA is given by the formula NA N12 N22. The NA is also related to the fractional index change, D, which is a useful parameter for calculating dispersion effects. Optical fibers are categorized into three main types. 1. Single mode step index. This fiber has a very small core diameter, 8 to 10 millimeters, and supports only one light propagation mode. Its key advantage is minimal dispersion, making it the ideal choice for long-distance, high-speed communication. 2. Multimode step index. With a larger core, 5200 millimeters, this fiber supports multiple modes. The drawback is that the multiple light paths cause significant modal dispersion where the signal spreads out. 3. Multimode graded index. This design addresses modal dispersion by using a variable refractive index profile. The index gradually decreases away from the center of the core, which effectively guides different modes so that they arrive nearly simultaneously at the receiver end, reducing dispersion. A complete fiber optic communication system follows a four-part process. 1. Information source. The analog signals, like voice, video, or data, are first converted into electrical digital signals using an analog to digital converter. 2. Transmitter. The electrical signal is then fed to the transmitter, which includes a modulator and a light source, typically an LED or semiconductor laser. This converts the electrical signal into corresponding optical pulses. 3. Optical fiber. The fiber acts as the transmission medium, carrying the optical pulses over long distances via total internal reflection. 4. Receiver. Finally, the receiver converts the optical signals back into electrical signals using a photodetector. This is followed by an amplifier and a signal restorer to recover the original information. Our second unit is dedicated to quantum mechanics. This revolutionary theory, which began with Max Planck in 1900, is essential for explaining the motion of microscopic particles like electrons and protons. It's the bridge between classical physics and the atomic scale. The core concept we explore is the dual nature of matter, where particles are understood to exhibit both wave and particle characteristics. This fundamentally changed our understanding of the microscopic world. In 1924, Louis de Broglie presented his revolutionary hypothesis. He proposed that just like light, matter also exhibits a dual nature. He called the waves associated with material particles matter waves or de Broglie waves. The key relationship is the de Broglie wavelength, L, which is inversely proportional to momentum, ph hmv, L hmv. This simple formula links the quantum world via Planck's constant h with the classical world via mass and velocity m and v, and is the mathematical expression of wave-particle duality. The de Broglie wavelength formula can be expressed in different, more practical forms depending on the context. 1. In terms of energy, E. Since kinetic energy E seemed V2, we can rewrite the formula as Loich 2 me. This is useful when the kinetic energy of the particle is known. 2. In terms of voltage, V. For a charged particle accelerated through a potential difference, V, the formula simplifies to the useful expression LMZ 12, 127, ViRO. This is frequently used for electrons. 3. In terms of temperature, T. For particles in thermal equilibrium, we use the temperature form LH 3mkBT, where Kb is the Boltzmann constant. The Davison-Germer experiment in 1927 provided the first crucial experimental evidence supporting de Broglie's matter wave hypothesis. They directed a beam of electrons emitted from a heated tungsten filament onto a nickel crystal target. The result was a diffraction pattern, which is a characteristic of waves. Specifically, they measured maximum electron scattering at a 50-degree angle with a 54 V accelerating voltage. The wavelength they calculated from the diffraction pattern, 1.65 OR, almost perfectly matched the theoretical de Broglie wavelength, 1.67 OR, conclusively confirming the wave nature of electrons. The very next year, in 1928, G.P. Thomson offered further confirmation. He fired electrons through a thin gold foil. The electrons created a pattern of concentric diffraction rings on a photographic plate. This ring pattern was virtually identical to the pattern produced by X-ray diffraction, and since X-rays are known waves, this provided powerful conclusive evidence that electrons also behave as waves, strongly supporting de Broglie's hypothesis. The Heisenberg uncertainty principle, established in 1927, introduced a fundamental limit to what we can know about a quantum particle. It states that it is impossible to simultaneously measure both the position and the momentum of a particle with perfect accuracy. Mathematically, the product of the uncertainty in position, dx, and the uncertainty in momentum, dp, must be greater than or equal to h for p. This limitation is a direct consequence of wave-particle duality. If we try to pinpoint the position precisely, tixuro, the momentum becomes completely uncertain, and vice versa. The principle replaces the certainty of classical mechanics with the language of probability in quantum measurements. While de Broglie gave us the wavelength, Schrödinger provided the wave equation, which is the mathematical description of matter waves. The time-independent form is shown here. The core of this equation is the wave function, pis. While Kex itself is complex and has no direct physical meaning, the square of its magnitude, Psatsitsern 2, has profound significance. It represents the probability density of finding the particle per unit volume. This probabilistic interpretation of the wave function is one of the key cornerstones that revolutionized atomic physics. The simplest and most illustrative application of the Schrödinger equation is the particle in a box model. When a particle is perfectly confined within a one-dimensional box of length L, the Schrödinger equation yields a profound result. The energy of the particle is not continuous but quantized. The allowed, discrete energy levels are given by n. The model provides us with the wave function, Poisson, Tau, and the probability density, Schacht-Schwerin x 2. This entire model is a clear demonstration of both quantum energy quantization and the wave nature of matter. Unit 3 shifts our focus to electronic materials. This theory uses the electronic structure of solids to explain their electrical, thermal, and magnetic properties. The modern understanding evolved through 3 historical stages: the classical free electron theory, the quantum free electron theory, and finally, the zone theory. Ultimately, mastering the behavior of electrons in solids is what allows us to design electronic devices and fundamentally differentiate between conductors, semiconductors, and insulators. The theory evolved significantly as quantum mechanics developed. 1. 1900, classical theory, Drude and Lorentz. This explained basic conductivity and Ohm's law, but failed when trying to account for specific heat or the temperature dependence of resistivity. 2. 1928, quantum theory, Sommerfeld. Sommerfeld introduced quantum mechanics and Fermi-Dirac statistics. This successfully explained issues like specific heat and thermionic emission. 3. 1928 Zone Theory. Bloch. This is the modern, most complete theory. Bloch developed the band theory using the concept of periodic potential. Critically, it completely and successfully explains the classification of all materials, conductors, semiconductors, insulators, and their electronic properties. The Fermi level, EF, is a central concept in solid state physics. It represents the energy level where the probability of finding an electron is exactly 21 at any temperature above 0K. This probability is described by the Fermi-Dirac distribution function. At absolute zero, T of 0K, all energy levels below the Fermi level are completely filled with electrons, and all levels above it are empty. As the temperature increases, the distribution broadens. This broadening allows thermal energy to excite some electrons into higher energy states, which is essential for understanding conductivity in semiconductors. The density of states, GE, is a mathematical function that quantifies the number of available energy states per unit energy per unit volume that electrons can occupy. The formula for free electrons is shown on the slide, where the factor of 2 explicitly accounts for electron spin. This function is absolutely crucial because we use it, along with the Fermi-Dirac function, to calculate the carrier concentrations in semiconductors, the number of free electrons and holes, which fundamentally determines a material's electronic properties. In a real crystal, the electrons are not truly free but experience a periodic potential. This is due to the regular repeating arrangement of ions in the crystal lattice. Bloch's theorem gives the general solution for the wave function of an electron in this periodic potential. To make this complex problem tractable, the Kronig-Penney model approximates the potential as a series of rectangular barriers. The crucial output of this model is the concept of allowed and forbidden energy bands, which is the basis for explaining the electrical properties of all solids. The band theory allows us to classify all materials based on the structure of their energy bands. Conductors. In these materials, the valence band and conduction band overlap. This means there are abundant free electrons available, allowing for easy current flow and resulting in a very low resistivity. Examples include copper and silver. Semiconductors. These have a small band gap, 1 to 2 eV. This gap is small enough that thermal energy at room temperature can excite electrons across it, creating some conductivity. Examples are silicon and germanium. Insulators. Insulators are defined by a large band gap, around 10 eV. This huge energy gap prevents electrons from being excited into the conduction band, leading to extremely high resistivity. Examples include glass and rubber. Our fourth unit, semiconductor physics, is arguably the most crucial for modern technology. Semiconductors have the unique property of having conductivity that is intermediate between conductors and insulators. Their key properties are temperature-dependent conductivity, the ability to be precisely controlled through doping, and the mechanism of creating electron-hole pairs for current flow. Mastering this field is absolutely essential, as it forms the basis of all modern electronics, from simple diodes to the incredibly complex integrated circuits that power our digital world. We classify semiconductors into two types. Intrinsic semiconductors. These are pure semiconductors, meaning the concentration of electrons, N, equals the concentration of holes, P. At 0K, they are insulators, but at temperatures above zero, thermal energy creates electron-hole pairs. Extrinsic semiconductors. These are created by doping the intrinsic material with controlled impurities. O-adding pentavalent dopants creates N-type semiconductors with an excess of electrons. O-adding trivalent dopants creates P-type semiconductors with an excess of holes. This process of doping allows for the precise, controlled conductivity necessary to build all electronic devices. The position of the Fermi level, EF, is a key indicator of a semiconductor's type and its concentration of carriers. In intrinsic semiconductors, the Fermi level is perfectly centered within the band gap. In extrinsic semiconductors, the Fermi level shifts toward the energy band of the majority carrier. Or in N-type, EF moves up toward the conduction band, EC. Or in P-type, EF moves down toward the valence band, EV. The exact position of the Fermi level is controlled by both the operating temperature and the concentration of the doping impurity. Semiconductors are also categorized by their band structure geometry. Direct band gap, the maximum of the valence band, Vb, and the minimum of the conduction band, Cb, occur at the same momentum value. This geometry allows for direct, radiative recombination, which efficiently produces light, photons. They have a high recombination probability and are used in all light-emitting devices, like LEDs and lasers. Gallium arsenide, GaAs, is a prime example. Indirect band gap. The Vb maximum and Cb minimum occur at different momentum values. Recombination here is non-radiative, typically producing heat instead of light. They have a lower recombination probability and are used in most logic and switching devices such as transistors and diodes. Silicon, Si, and germanium, Ge, are the best known examples. To conclude, the principles of applied physics are not just academic, they are the direct engine of technological innovation. Quantum mechanics is enabling the development of the next generation of computing with quantum computers and the security of quantum cryptography. Semiconductor physics is the foundation for advancements in artificial intelligence and the increasingly crucial field of renewable energy. Optical technologies continue to revolutionize communication and medical procedures. Ultimately, a strong understanding of these fundamental principles is what prepares you, as engineers, to tackle future grand challenges in areas like nanotechnology, sustainable energy, and advanced materials, which will undoubtedly shape our world for decades to come. Thank you.